And it's, oh, you got the recording going. Okay. And the RMS emittance is just, for instance, if you're just looking at 2D emittance, it's a combination of the variance in position and in angular spread or transverse momentum. And so the idea is that if you have just a 1D phase space here, we have position on the horizontal axis and angular spread or momentum on the vertical axis, your beam is going to occupy some volume in that phase space. If you have a very high brightness beam, then you have a lot of electrons centralized into this small volume. And if you have a lower brightness beam, maybe you have the same number of electrons, but they're spread in this larger volume. So the gist is if you want a high brightness or you want a high brightness, and that means you want to know where your electrons are and you want to know where they're going. And so there are a lot of applications that benefit from having a higher brightness, and this is a very truncated list here. One instance are electron microscopes, albeit with very low current. You really do benefit from having an idea where your electron is. And then in free electron lasers, they do benefit from having a very high brightness as well. I believe their fluence is limited by brightness. And one quirk about brightness, this is really more of a quirk about emittance, is that your RMS emittance is conserved under linear fields. So if you send your beam through a bunch of quadrupoles, like a photolattice, you'll typically mostly conserve your emittance. So for instance, we have some emittance or phase space volume here, and then we go through some process that might be really weird, but as long as it was linear, you end up with essentially the same emittance, even if it's like a little bit skewed in phase space. However, linear fields are not the only things that electron beams experience. There are nonlinear processes that often worsen brightness, such as space charge. Oh. Okay. There are nonlinear processes such as space charge will typically make your beam explode, for instance. So that's something you might want to mitigate. But the gist is that if you want to have a high brightness at the end of your beam line, it's really good to start with a very high brightness at the beginning. So I'll talk about how we can get that. This is going in order from least relevant to most relevant for my work. First off is decreasing response time. If you're just using a standard photocathode, your illuminating laser is going to penetrate some depth into your material. Your electrons are going to be excited from that depth and will take some time to return to the surface. So even if you have like an ultra-fast femtosecond scale laser, that could be spread out to hundreds of femtoseconds or picoseconds. And so if you want to improve that, you do have to just pick a better material or a different laser wavelength to get a smaller skin depth or so that the transport process is faster. Oh, I didn't do that. Okay, another way of improving brightness is by decreasing the mean transverse energy. This is a really common term in the photocathode group in CVB, but it's less common elsewhere. It really is just the average transverse energy of your beam, where the longitudinal direction is where your beam is going on average. And so if you have a lower mean transverse energy, then you have a lower transverse momentum spread and therefore a lower emittance. And so if you just have like a normal flat photocathode, to improve your MTE, for instance, you want it to actually be atomically flat. If you have any imperfections like shown here, you're going to get emission in these weird directions, which will generally increase your MTE and worsen your emittance. Additionally, you can tailor your material to do this as well. And lastly, this is probably the most important for my project, is just flat out increasing the current density of your emission. And so to do this, you can choose a material with a high quantum efficiency, which means you can send in more photons and get more electrons out for each photon, or you'll only get one electron at most per photon, but a higher quantum efficiency means you get less loss, and you can illuminate it with a stronger laser. Or you can do what I'm doing, and that is just enhancing and focusing your fields to a very small area to get a very high current density. This is not what I'm doing on the right here, but this is a spiral plasmonic cathode. You illuminate with a laser, and it plasmonically enhances fields at the very center of the cathode, which enhances and localizes your ionizing fields. So another thing that I want to talk about is field emission. It's sort of underlying our laser field emission cathodes, so it's good to talk about. And by field emission, I mean we're taking a cathode and you apply an electric field to it, and electrons can tunnel out into vacuum. So it's probably one of the simplest type of cathodes. And one cathode that I like to show off or like to talk about are these velvet cathodes. And by velvet, I mean velvet that you can buy at the store. This is just a very classic beam source. The fabric structure of these velvet cathodes are like a lot of little nanotips in a way, a lot of little lightning rods. And so they enhance your local fields and give you a stronger, or you get more current because of that. But it is also like a lot of disordered lightning rods. So you're not going to get a very good emittance or MTE from this, even though you do get a very high current. The sort of opposite end of that spectrum field emission are these nanotips. So these are pretty common in electron microscopes, for instance. You can illuminate them with a laser or an RF field, and you'll get cold field emission from like a 10-ish nanometer area. And because of that, you'll typically get very good emittance, albeit with very low current. But that's usually okay because oftentimes you only want one electron per pulse anyway. If you do want more current, you can turn up the field to an extent, but these nanotips can be quite fragile. So you might need to use an array, but that doesn't really help you with emittance. So there's some limitations to this, and I'll go into that a little bit in a little bit more detail here as well. So one problem with these nanotips is that the apex is sort of spherically shaped. And so that means that your ionizing fields are going to be mostly enhanced at the apex, but also you're going to get some enhancement off the apex somewhat. You're going to have fields that are pulling electrons out at these angles. And the thing is, this is happening in both dimensions. So this process is going to worsen your MTE in both the X and Y transverse dimensions. Additionally, if you're doing laser field emission from these nanotips, like ultrafast 800 nanometer laser field emission, you can get peak fields like tens of gigavolts per meter, maybe 40 gigavolts per meter, which is actually pretty impressive, but we can still do better. So now I'm finally getting to nanoblade laser field emission cathodes. This SEM image sort of brings upon an optical illusion, but I'll get rid of that right now by pointing out that this is the apex ridge of the nanoblade, and there is a second nanoblade next to it. And these are sort of valleys in between the nanoblades right here. And so this ridge structure, much like a nanotip, will enhance and confine fields plasmonically to the very apex. So that means we can get very strong fields without having to have an insanely powerful laser. Additionally, one dimension is flat. So in this direction along the nanoblade, we do not get that extra MTE contribution from the curvature that you would normally get from a nanotip. Another point is that they seem to be more thermomechanically robust. Determined by experiment, we've observed surface fields up to 80 gigavolts per meter, whereas nanotips I mentioned before only got up to maybe 40. And so that's a factor of 4 in intensity. So that is a substantial improvement. Lastly, this is more of a quirk than a feature, but maybe it is a feature depending on what you want. These produce flat beams. And by flat, I mean that one transverse dimension of your beam is much larger than the other transverse dimension. And so this could be useful for accelerator on a chip or dielectric laser acceleration. But if you don't want a flat beam, then you can just do some accelerator physics manipulation further down the beam line and turn it into a round beam. So I did specify laser field emission. Why am I talking about laser field emission and not static field emission? Well, both tips and nanoblades cannot withstand these strong static fields for long. Even with RF fields, you can start to get damage as you get Joule heating at the apex, which eventually overheats it and melts it. And so if we instead use an ultrafast, which is like fuse cycle 800 nanometer laser, you can actually get to a higher surface field and therefore a higher peak current, while also circumventing damage as you're not depositing so much energy into the structure. There are also another couple benefits of this. Because of the laser profile near the apex, you get near field gigaelectron volt per meter scaling of or near gigaelectron volt per meter scale Parmod forces, which help to extract electrons from the surface. And you also get a broad emission spectrum, which similarly helps to increase yield. So this is laser field emission. So there's going to be some interesting dynamics going on near the surface. If you just had static field emission, you'd emit electrons and they just leave the material, and that would be the end of the story. But in this case, with a laser, the field is oscillating, so there's a little bit more going on there. In this picture, we have time in the vertical axis going downward, and your metals are initially living within the material, or the electrons are initially living in the metal over here on the left. As the laser field propagates and increases in intensity, you can see once the field is actually pulling electrons out, the electrons can tunnel into vacuum and propagate. Some electrons will just emit and never return to the material, and those are called direct electrons, and they make up the majority of your spectrum. Some of the electrons will return to the material, and some will elastically scatter off the surface, and those can attain a higher energy due to that process, and those become the rescattered part of your spectrum. And those go up to about 10 times the Parmo potential of the field. Then this process repeats for each cycle of the laser, and so in a sort of semi-classical picture, you can interfere those different contributions and give you your h bar omega peaks that would normally correspond to the multi-photon emission order. Okay, I'll pause for questions briefly if anyone had any questions on that. This is sort of a natural pausing point. Wait for a few seconds. Okay. So I have a few projects I'm going to talk about. Firstly, this material normal energy distribution, or MNED project, which is sort of studying the fundamental field emission underlying this process. And really it's studying what the electrons are doing within the material and how that affects their ability to field emit. After that, I'll talk about this 11 UP project, which is sort of looking at this classical rescattering model near the nanostructures and how the inclusion of the field drop-off induced by the nanostructure affects what we get out of the system. And then lastly, I'll talk about what's probably been my focus for at least the first few years of my PhD, this time-dependent Schrödinger equation calculation modeling laser field emission with image charge trapping. So I'll get into the first one. So I've been going back and forth between photoelectric effect and field emission and laser field emission. At this point, I feel the need to justify why we can look at field emission if we're really illuminating the structure with a laser. There are a lot of, I shouldn't say a lot of, there are several sort of checkboxes we have to check off to make sure we can actually do this study, but probably the biggest one is the Keldysh parameter. This sort of delineates this quasi-static field emission regime where we want to study a system from the multi-photon or photofield ionization regime, which is sort of like your standard photo emission process. And this Keldysh parameter is mostly just a ratio of your ionization potential to the Parmo potential of the field, which is proportional to laser intensity. And so if you have a very weak laser, then you might expect to observe multi-photon absorption as opposed to field emission. And on the other end, you might expect, if you have a very large Parmo potential or intense laser, you might expect field emission. So if we plug in our values, 80 gigavolts per meter, 800 nanometers wavelength, we get a Keldysh parameter about 0.2, which is much less than 1 in air quotes. So we can sort of study our system a little bit using field emission, quasi-static field emission. Even though there's some dubiousness because of that, there will be some applicability, or we expect some applicability spillover for RF cavities, because if you're studying breakdown starts with arcing, and arcing comes from field emission due to the RF field. So yeah. To start off with some basics of field emission, the most common framework to study field emission is the Fowler-Nordheim framework. Essentially, you have a bunch of occupied states within your material, which for a good metal like gold or copper really do look similar to just like a free electron gas state. And each of these states is going to have some probability of tunneling into vacuum when you apply a field to your surface. And so it turns out that the probability of tunneling is mostly dependent on the normal energy of your state. And the normal energy is just the total energy minus the transverse kinetic energy. And so if you want to find the number of electrons that you get out of your system, or the total current you get out of your system when you apply an electric field, you have to integrate the probability for each normal energy to tunnel with the actual source current within your metal at each normal energy. So that's sort of this integral down here, where we have the probability of field emitting for each normal energy, the current with respect to the normal energy, and this distribution here is what we're calling the MNED current, or material normal energy distribution current. And this is really just something that you either have to use some sort of like free electron gas model to calculate, or density functional theory. So to start off with, we of course use the free electron gas. We're studying a gold-coated nanoblade, so it should work pretty well. And I don't want to go into too many details on the calculation here, but you're just integrating over slices of the Fermi sphere, and you can get an MNED current that is just a linear function of the normal energy. Additionally, the mean transverse energy you get intrinsically from the material is a similar function of the normal energy. And that's great and all, but how does this apply to real materials? So on the right here, I have a really funky Fermi surface. This is a calculation of tungsten. And it might be hard just to sort of read off, oh, what would the MNED be for this structure? It turns out that we can have, for relatively low applied fields, we can just use this very simple heuristic where we draw a vector from the center of the reciprocal space out to the surface normal. It intersects the Fermi surface, or sorry, every time it intersects the Fermi surface, you get one contribution of the free electron gas. So in this case, it intersects 4 times, so we get 4 times free electron gas. That's what we would expect. But I did specify this is for low field. For laser field emission, where we have 80 gavels per meter fields, the decay width or the sort of the depth of energy where we're sampling in this field emission process is like 3.6 EV. So this won't work so well for laser field emission, but for RF, it should work out okay.
Joshua, one quick question. I want to be, I think people, I'm pretty sure people in this audience are not too used to what a Fermi surface is. Could you zero in for a second and explain what that is in layman terms?
Yeah, so, okay. So to start off with, in a metal like gold, you have crystal momenta, which is essentially just the block wave vector for each quantum state. So this is going to be a bit messy. Let's see. Essentially, your crystal momentum, it really is like the momentum of the semi-classical momentum of your electron in a metal for each state within the reciprocal space. And your Fermi surface tells you, sort of bounds the volume where your electrons actually live. So outside of this Fermi surface of this the red one here, if we were over here, if we're looking at a state that's occupying this space here, at 0 temperature, we would not expect that electron to be occupied, or that space to be, that state to be occupied. And then if you're inside the Fermi surface, that state is occupied. And so when you're doing all solid state physics and you're sort of looking at perturbative processes that can be treated as linear or weak, you can sort of look at what's going on near the surface, because that's typically where interactions are going on. If you're deep within the Fermi surface, then there's not really a lot of space for electrons to move around. You have the Pauli exclusion principle. And then if you're at the surface, you can excite a little bit and that you can actually have something going on. So that's the sort of gist of the Fermi surface. If anyone has more questions on that, I can go into more details on that. But otherwise, I'll continue. Okay, so it might have been good to start with a Fermi surface that looks like this, because this is a lot cleaner looking and a lot nicer. But this is the MNED I calculated for copper via DFT. And essentially, if you want to use a DFT result to get the MNED, you just have to integrate over the entire Brillouin zone within your material. In my case, I use Monte Carlo and Wannier interpolation if you're interested in those details. But we can actually look at the results here. This is represented as a ratio to the free electron gas contribution for 100 and 110 surface normals, which is just sort of the orientation of your lattice on your surface. We get basically 1 times contribution, and that sort of makes sense. This is the only Fermi surface for copper, and in the 100 and 111 direction, there's just one intersection. And the 111 direction, there's something really weird going on, and that's due to this Bragg plane intersection. That's another solid state physics term, but the gist is that if we have this if we have something weird like this, we'll have to take other things into account. In this case, it turns out that this increases the effective work function for field emission by a very small amount, probably not super detectable, especially considering various experiments trying to measure work function will give you different results. But this sort of exists, and it's quite interesting. We're hoping to see if other materials will have this as well. And if we're going back to the chromium group or this tungsten Fermi surface, we can go back to that 100 result and see that, in fact, we do approach about a 4 times scaling for the free electron gas current. So that's a nice result. And of course, we have some upcoming work for this as well. I did specify that the tunneling probability is going to be mostly dependent on the normal energy of your state, but it might also be dependent on the transverse crystal momentum of your state. We're not sure how much yet, but that's why we want to investigate this. Additionally, we want to calculate this MNED for all the transition metals. That's a big project that we're sort of embarking on. But we're hoping to see if maybe there's a metal that doesn't field emit so well, or maybe even an alloy that doesn't emit so well, or maybe one that does emit very well. So each sort of side of that spectrum will have different applications. However, in our case, this has all been a pretty big aside, and I think it will be mostly applicable for RF cavities if we do find something. It turns out for laser field emission, the vacuum dynamics end up being more important once we get to these very, very high fields. This image charge trapping sort of muddles these details of where your electrons are coming from. So I'll pause there again if there are any questions. I'll give a few seconds. Okay. Okay, so yeah, now I'll get to some of the classical dynamics in vacuum. This will probably, I think this one will be a bit more approachable, having not seen it before. So yeah, classical rescattering, just to give you an idea, it sort of looks like your electron will tunnel into vacuum at some point and experiences the laser field, kind of like I had in that picture earlier on in the background, and it might emit directly into vacuum, or it might rescatter and also emit. And to give you an idea of the energy scales here, the work function of these materials is typically like 5-ish EV, whereas this Parmo potential for our peak fields observed is like 50 EV. So the dynamics here are going to be quite important to study this emission process. So previous results had already shown what the sort of limitations of the system is classically for a uniform field. There's a peak energy of your direct electrons, which goes up to 2 times the power mode potential. The rescattered electrons can have to about 10 times power mode potential. And if you're looking at HHG, you can attain about 3.17 times the power mode potential in energy. However, we are near a nanostructure, and so we'll want to include some sort of field gradient. And so we basically just have a let's see, how do I want to put this? A deceptively simple looking differential equation here, where your electron experiences the acceleration due to the dipole laser field with some spatially dependent function g, and that is sort of the field profile induced by your nanostructure. Our initial conditions are that the electron tunnels into vacuum at some t naught, and we just assume that has 0 initial energy at t naught or 0 velocity at t naught. And we also have the rescattering condition. If the electron is at the surface, then it will reflect. And so we have various profiles we're considering. There's this exponential profile, which is a very common surrogate for just studying the system in general, but it also is applicable for plasmonic fields on a flat surface. There are these nanotip profile. There's this nanotip profile, which sort of goes like a 1 over r squared. And there's this nanoblade profile, which goes like more like 1 over r. So here's the sample results. On the left here, this is the uniform field result. This is the emission energy in black and blue as a function of your emission phase. And you can see that without any inclusion of any field gradient, we get up to about 10 times the power mode of energy in our emission energy for the rescattered electrons. If we increase the field gradient somewhat, in this case, delta equals 5, with delta being infinity equating to a uniform field. So this is a slightly perturbed field. We can see that the peak energy only goes up to maybe about 8.5. So we're sort of quenching the amount of energy we can get from the system by including a field gradient. And then if we go up to a field gradient corresponding to if we go up to a field gradient corresponding to an adiabaticity parameter of 1, which would be a really insane field, we get quenching of energy down to maybe like 3.3 times the power mode potential. So including this field gradient can be quite important. And probably a more useful plot is this one, where we're plotting the peak energy observed as a function of that adiabaticity parameter. On the left, we have a uniform field, and on the right, we have a non-uniform field. And you can see that by increasing the field gradient, the peak energy observed in blue here is decreased. It also goes up to a different value from before. Before, the uniform field result was 10 UP, but here it goes up to 11 UP. And that has a pretty straightforward explanation. When you include a field gradient, there is a slight Parmov force that once you go all the way out to infinity, you get an extra factor of the Parmov potential. The real question is, how is this fair? So this is the time-dependent Schrödinger equation calculations that I'll be getting to a little bit. This is the spectrum as a function of the laser wavelength. And so you can see that our calculation here, the black dashed line compared to the standard 10 UP result, the black dashed line tends to correspond much more closely with the actual cutoff compared to the standard 10 UP result. But one important thing to keep in mind here is that this is increasing the wavelength. The Parmov amplitude, or how far the electron will oscillate into the vacuum for any given wavelength, is related to the wavelength squared. But only the field to the power of 1. So if we stay with our 800 nanometer laser, we're probably not going to have to worry about this too much. But if we go up in wavelength, then this the field profile will have some substantial impact on the dynamics. There's some upcoming work for this. Firstly, two-color control. It would be pretty natural to include this in our calculation. It's basically, we have our 800 nanometer fundamental mode, and we have the 400 nanometer second harmonic, and we can tune the phase and relative intensity of that second harmonic to, say, optimize the chirp in HHG, or see what else we can do with that. We want to see what the inclusion of a static field does. Firstly, that's a sort of crude approximation to including the image charge potential, and also our nanoblade is going to be living in an RF field most likely, so we'll also want to see how that might affect the peak energy we can get out of it. And lastly, we want to include the collective image fields. The TDSE code kind of does this naturally anyway, but we want to be able to look at these individual particle trajectories and see if we can get the same result classically. So again, a nice pausing point if anyone has questions.
I did want to know whether there is a plan to verify some of these models of laser scaling laws by looking at a single color, but sort of extending, as you mentioned, the wavelength, like going into the 3 micron range.
Yeah, a long time ago, James was talking about 10 micron. And at this point, I'm not entirely sure. Experimentally speaking, our nanoblades are just waiting to be moved to where the laser now lives. So once that happens, maybe. But right now, I don't think we have any specific plans.
I see. Yeah, that might be, if that's, I mean, that's something that could be done easily at, with the test of an OPA, with pH, for example, and our laser in our lab has, tunability already up into the 15 micron range or so, with intensity limitations, but it's relatively continually tunable.
Yeah, it's kind of interesting because there's a lot of factors going on there. We get these strong fields from plasmonic enhancement, and how well the laser couples to the surface plasmons will probably factor into that somewhat. And yeah, we do need some laser intensity, but the nanoblades offer a lot of enhancement, so I don't know how weak we can go. Yeah, it's kind of up in the air right now. Not too sure. Okay, I'll move on to the last project. This is what I had been focusing on for the past several years, modeling the system with a time-dependent Schrödinger equation. Of course, the system is going to be most accurately represented quantum mechanically, although trying to include the photons quantum mechanically as well would be quite difficult. So I just use a dipole approximation for the laser/plasmonic field. And some unique attributes of my code are that it's a non-interacting ensemble calculation. So most calculations will just use the electrons at the Fermi level, but I am including electrons at the Fermi level and below. There's also the inclusion of the field drop-off, which most calculations don't include, or actually I don't think I've seen a TDC calculation that includes it yet, other than my own. And then the collective image potential for these accurate yields. It's quite important to get for these yields, but it's not technically TD-DFT. I'm not including any exchange correlation functional. even though this image potential is a density functional. Okay, so here's the simulation setup. On the left, we have an SEM of the blade. There's a sort of nodule here that makes it look not very cylindrical at the apex, but I believe that's due to the fact that we had to cut the blade to actually take the SEM. Either way, the blade is roughly cylindrical at the apex, and our field enhancement is going to be mostly localized there. And so if we want to go to the cartoon over here, this is what the system sort of looks like zoomed out, where our field enhancement is maximized at the apex. And so we want to choose our simulation axis along that apex. This is just a 1D simulation. And then our electrons will be moving up and down along that direction. So of course, we're doing the time-dependent Schrödinger equation with a dipole field. So we need some sort of potential for the electrons to live in. So we can zoom in and see what that is. For the surface potential, I just use a Jellium surface. And what that looks like on vacuum is like this 1/r scaling for the image potential. And within the material, it's more like a sigmoid function, which is a DFT result. And then on the back, it's just a polynomial spline to minimally reflect electrons that are at or above the Fermi level or the vacuum level. To initialize the calculation, we fill up the states up to the Fermi level and apply a harmonic field. This is just a finite difference time domain calculation done some time ago for the gold nanoblades. You can see it includes some field drop off and also some field penetration within the material. If we're including the image charge, the collective image charge, it's pretty difficult to try and include the full blade geometry when we're only doing a 1D calculation. So to do that, we're sort of taking the cylindrical apex geometry and mapping this 1D calculation onto that. So each position in our calculation is going to correspond to one of these cylinders. And what's nice about this model is that this cylinder will completely shield its image charge from the outer cylinders. So this ends up being a nice order n integral to calculate the potential as opposed to n squared that you might normally expect. So we can run the calculation, and this is what a result might look like. This is the electron density as a function of space or position and time. So you can see initially our electrons live in the material, but centered at 150 femtoseconds, our laser is maximized, and you can see electrons will tunnel into vacuum and go through this process. It's kind of fuzzy because it was not a very smooth. It wasn't a very zoomed in picture here, but you can sort of see what's going on vaguely. And then some of the electrons will emit into vacuum going up this way. And you can also tell, possibly, depending on the monitor you're looking on, you can see some of the electrons are falling back to the material with these sort of bands here. And so that tells you that we're including the collective image potential because these electrons are being pulled back in by the collective image charge. So, of course, we want, this is probably the...
one quick question in these simulations, are you keeping track? I mean, here it does look like you're integrating according to all potential emission K vectors, but are you keeping track of the momentum of each of these electrons, meaning not only the energy in which they exit and when phase, but at what trajectory they follow?
So can you repeat the question?
Yeah, basically any given one electron, right, exits into vacuum and follows a trajectory, right, whether they're exiting, in what direction they're exiting off of the surface, right, whether they're perpendicular or maybe at an angle, are you keeping basically that momentum vector for each electron or any microparticle that simulates the ensemble of electrons, or is this information lost in these calculations?
So are you talking about like the transverse momentum?
Yeah.
Yeah, it's sort of built. The most I can really do here is sort of go back and get that mean transverse energy, for instance, for each energy level, because each energy level in this case corresponds to a normal energy. And so when I do some calculations for the intrinsic MTE, for instance, that I sort of build upon that. But beyond that, it's sort of kept constant. The transverse momentum it does not change.
I see. Okay, yeah, that helps with interpreting these results a little bit. Yeah, thank you.
Yeah, I can focus on that a little bit later too. It should be in a few slides. Yeah, so probably the most important result here is the total yield On the right here, we have our experiment interlongin for the tungsten-coated nanoblades. At low laser intensity, the yield follows this 2.5-ish power law, which corresponds to the photon order you would expect. And then at very high fields, it tapers off to this linear scaling. The number of electrons you get out is linear with the number of photons you put in. And so we justified that by sort of equating the Parmo force to the space charge force, pulling the electrons back in, or the collective image force. And so that was mostly satisfactory, but we had to actually test it. So on the left here, we have my TDAC calculations. In black, this is without any image charge included. While it does taper down to a power law of about 1.5 or 1.75, that's due to channel closing, not the collective image potential. So it's not quite explaining the whole picture. When we do include the image charge in our calculation, we get a power law in blue that is about 0.96. So that's much closer to 1. So this is a nice explanation, or it shows nicely that including the image potential will give you this linear high field scaling. And I don't want to go into this slide too much, but this is sort of a more analytical way of looking at the system where you correlate the electron position with their energy, and you can actually come to the same conclusion that the emitted charge is proportional to laser intensity. So this is getting into some of what you're talking about a couple minutes ago. Of course, firstly, we're going to get some MT due to the curvature of our blade. And that's because our blade is curved and we're going to have some field emission going in this direction, but also in this direction, in this direction, in this direction. So the way that I did this was just by taking this 1D calculation and repeating it for each angle, or really for various fields. And we can get this angular spectrum. So this is the spectrum of your electrons as a function of the angle around the apex. So at the very apex, we get the highest energies and the most yield. But as we go around to where there's lower field, we get a lower energy of emission. And so we can integrate over this to get our total spectrum. This plot is pretty messy, so I'll try to walk us through it a little bit. We have the yield here in black. That is, we have the direct part of the spectrum, the plateau, and a final drop-off. And this is going from energies from like 0 to 500-ish EV. So this is a very large field calculation. We'll have some mean transverse energy due to the curvature, like I've shown here. And most of it's going to come from the center of the direct part of the spectrum and the center of the plateau. But you do get these nice little dips at the end of the direct part and at the end of the plateau, just because you're sampling just this little tiny bit where you still have a relatively high current, but not a large energy spread transversely. There's also the intrinsic MTE. So each electronic state is going to correspond to some mean transverse energy that will contribute to the final beam. And you can just integrate over what each electron state contributed. And we find that the intrinsic MTE is on the order of like 0.5 to 1 EV. So it's quite large compared to what most photocathodes are doing, but it's sort of counteracted by the fact that we're getting very high current densities from this. So we can integrate over this whole spectrum and try and get some estimates of brightness. And so the one value I want to focus on here is this 5D brightness for this full spectrum that's not sampling any particular part and including the image charge force.
Just another quick interception for those. It might be helpful to have a quick intuitive understanding of what the 6-dimensional brightness and the 5-dimensional brightness is for folks here.
So yeah, 6-dimensional brightness. Okay, I should start with 4D brightness. 4D brightness includes both your transverse dimensions. So you have emittance due to, say, your X position spread and your X angle spread or momentum spread. And then the same thing for your Y. So that would be a total of 4 dimensions, 4D brightness. If you go to 5D brightness, I'm just looking at the units here. I believe that is because you're including the... Oh yeah, it did get a bit tricky here. I'm kind of blanking on why it did exactly. But part of what's included is the length of your beam. So how long it is physically, or if you're relativistic, it's the same thing as how length and time also. So that's why this is amps per meter squared radian squared. If this were 4D brightness, it would be coulombs or number of electrons per meter squared radian squared. 60 brightness, I think I need a little bit of help on that one. I included like a weird factor of the energy.
Yeah, you basically now add sort of the energy spread, or the, if you keep working in time, sort of the moment, the derivative of time, right? Like the spread in the longitudinal dimension.
Right. Yeah. So that one ended up actually being a fair bit worse because there is a large energy spread here. But here, if we just use the length of time of the laser, this is how we get this value here. And so this ends up being 10 to the 18 in SI units, where state of the art is something like 10 to the 16. So it's quite promising, but there are some issues notwithstanding with this calculation. Firstly, I'll point out that the simulation versus experimental spectra are quite different. This is for a relatively low field, actually. If we expected the spectra to be a lot closer and sort of, at least qualitatively, the plateau here would probably start up here and have a relatively high intensity. And so to mitigate that, or to help that, I need to work on the surface potential. And so that's part of this upcoming work. Mostly done, but I want to optimize that surface potential. I was thinking to match a Lee experiment, but right now I'm thinking I'm gonna have to go a more ab initio approach. Additionally, there's surface roughness that the Erlangen experiment had to consider. Although our nanoblades are much smoother, so that may not be an issue. And lastly, this is sort of an aside to the TDSE, but will also help inform the TDSE code, and that's looking at plasmonic enhancement. We know we're at very high field. We're probably gonna have to include the nonlinear Kerr effect. We're gonna have to include the fact that electron distribution heats up to something like 30,000 Kelvin. And that will affect the dielectric constant, for instance. So that also has to come into play. So it's going to end up being a somewhat messy system there, but that's probably what's going to be the rest of my thesis. So some quick takeaways. Nanoblades seem to be promising high brightness cathodes with applications high harmonic generation, even though I didn't mention that too much here. And I'm hoping we'll have some nanoblade measurements soon with spectra, yield, and survivability once the experiment actually moves to where the laser is. And so, yeah, and then these upcoming calculations will help us to improve these systems further. So I'll leave some space for some final questions now. 10 minutes, and it being a bit longer than expected.
Yeah, no, thanks, Joshua. This is really useful. Yeah, I think as he's mentioned, we could any general questions about this. Just to give you a bit of background, some people here in the audience are working in electron beam sources, either at LCLS2 or right here at UCLA with DC guns, and some others are not at all. And so I think you have a broad spectrum here of expertise. But anyway, yeah, anybody has any questions or comments for Joshua? It was all perfectly clear. Can you
One
tell
quick
us more?
question.
Oh, yeah, go ahead, Jack.
Nice talk. So I was just curious if y'all try pushing any of the wavelengths shorter for what y'all are studying. I mean, I know you talked about wanting to do any tests towards, well, you're mostly at 800 and then pushing higher, but I was curious about the other direction.
Yeah, so this brings me back to a meeting that I had probably several years ago where I showed off a plot that included 600 nanometers, and Jamie was like, who ordered this? Why are you doing 600 nanometers? So if I recall correctly, just going to lower wavelength, it's I just haven't been thinking about it that much. I don't think it's too useful for us because part of what we're doing is HHG. So okay, I'll sort of separate these two things. In HHG, we want to sort of maximize the power mode potential that we have because that seems to maximize the energy that we can get out of it, or the broadband bandwidth. And going to a lower wavelength decreases the power mode potential. So HHG, we probably don't want to go down in wavelength. For electron emission, I think that we'll probably just have to come down to how plasmonic enhancement works out. Yeah, we haven't been working on that too much.
I think that part of the answer goes back to some of the earlier. Well, you haven't done any of the theory, right? Because it's I think the context that maybe people were missing is this HHG focus, which is funny because you don't really talk much about it. But yeah, of course, if you start approaching sort of the work function of the bang up, right, of semiconductors and of metals, you start having a relatively different sort of model that you should be following, not really look at it from a field emission standpoint, but more from like single photonization standpoint, right? And then if you keep going shorter, you can now have, electrons or emitters or electron hole pairs being formed with, energies from far below the conduction band, for example, the valence band, right? And so I think some of your models will start breaking down the moment you start going really, really short. Right? And at that point, excess energy from photonization would start dominating on the amount of excess energy of electrons as well, right?
Right. Yeah, it gets harder. Let's see.
Yeah, maybe can you give us a bit of background? I mean, I know that I know quite a bit about it, of course, but can you give everybody else a bit of background on how this taps into HHG?
Right. So I think the best slide to talk about that is probably this guy. So when you have, okay, so for HHG, what you really want is some sort of oscillator that has a non-harmonic aspect to it. So in our case, we're oscillating the surface electrons at the surface, but there's also these atoms that they can interact with. And when they collide with the atoms, you get this Bremsstrahlung-like radiation. And what ultimately it looks like that oscillation has some not, I shouldn't say non-harmonic. It has higher orders to the harmonic. So in our case, okay, so for HHG, you just need to be able to do that process. And most people have been working with gas HHG. And with gas HHG, you just illuminate some gas with a very powerful laser. Your electrons will ionize into the vacuum and then rescatter with the atom with some energy and emit a higher energy photon. But of course, if you want to get higher and higher energies, you have to turn up the wavelength or the field. And by doing so, you push the electron further and further away from the atom, which can dissociate it, and you end up losing intensity. I think it goes down like wavelength to the power of 6 or something like that. So it gets really hard to drive HHG from a gas like that. From a metal, it's comparatively infinitely large. Like if you emit an electron and it comes back, it's going to hit something. So in our case, it's really interesting if we can get HHG from a metal, just because we don't have that 1 over lambda to the power of 6 scaling. And so that's part of what I initially started doing, but then my funding source became the Center for Bright Beams. And so my focus became electron emission.
Yeah, but basically you get and these graphs is really useful, right? You get the signatures from what you expect from traditional HHG, right? And the Horner multipotential scaling. What other advantages do you have other than it being a metal by using a nanoblade?
So let's see. One aspect is that you have an extended structure. So for instance, you could do HHG from a nanotip, but the interaction area is so small that you don't have a lot of participating charge. And so you're not going to get a large yield for HHG. For a nanoblade, it's extended, and so you're going to get participating charges all along the apex. And so in that way, you have much larger, you'll have a much larger yield. That's the first thing that comes to mind. Is there anything else you had in mind for that?
I think there was also an interesting, I never really understood this from your defense. There was some argument that Jamie was trying to convince me and Pietro on the symmetry of the emission based on the heat dissipation. Basically some effect of heating that the needle could only, for example, the needle could only dissipate in one direction, right? Versus the nanoblade being able to dissipate at least cylindrically. and you know, infinitely in one direction along the blade. And I guess I bought it, but I didn't fully grasp that argument.
So even without, I'll try to defend that argument in a second, but even without that, we do know that tips or blades have been able to get to surface intensities 4 times that of tips. So even just that's really the main thing, is that we can get higher fields and therefore larger primary potentials and yields compared to tips. The heat dissipation thing, it is really hard to explain. It was initially a counterintuitive result, which is part of why it's hard to explain. But the gist is that if you look at the heat equation, essentially the decay time for the heat equation depends on the number of dimensions that you can dissipate heat through. So you get a factor of 1 for a tip because it's effectively 1D structure. And for a blade, the length of the blade is uniformly illuminated, effectively, thermomechanically speaking. But it has 2 dimensions because of its large opening angle. So you can dissipate heat through 2 dimensions instead of just 1 for the tip. And because of that, you get that factor of 2, which ultimately means we can get a higher surface field.
That I buy, yeah. Maybe I just have a confused memory. There was something there that felt sticky at the time, but
I gave a really weird explanation at first, and then that's when Jamie butted and was like, "Oh no, we'll talk about the actual system."
Gotcha. Oh, we're almost at the top of the hour. Is there any other questions from anybody? Well, then if not, let's thank Joshua for coming here, volunteering his time to educate us on these frameworks and his calculations. And you know, hopefully we get to interact with you as you continue to do some of this work. You know, our groups collaborate. So anyway, with that, thanks again, Joshua. We'll stay in touch. Yeah.
Thanks for having me. I'll send you slides so you can pass them around.
Perfect. Thank you so much. Yeah. All right. Have a good one.
Bye. Thanks.